So last time we were together, when we weren't in lab anyway, we were discussing, sorry, when we weren't talking about exam stuff anyway, we were talking about Le Chatelier's principle, the principle of how chemical reactions respond to disturbances in their equilibrium. And we had talked about changes in concentrations of reactants or products. We'd also talked about changes in temperatures. You got to see examples of both of those kinds of phenomena in the lab, which I hope was sort of helpful in piecing together like real life examples. All right. You also saw a phenomenon where a changing concentration of H3O plus in a reaction or of OH minus in a reaction didn't end up actually changing the pH of the solution very much. Yeah. So the entire reason that, I mean, hopefully you've heard of buffers before. Buffers are solutions that resist changes in pH. But the entire phenomenon of a solution being able to resist a change in pH is strictly due to Le Chatelier's principle. So that phenomenon can be explained based on Le Chatelier's principle. So we'll talk about that a little bit today. The last one of the new kinds of examples, the new kinds of disturbances to equilibrium that I want to talk about, though, are changes in pressure for gases. So to do that, we will look again at the most important industrial chemistry reaction that exists, the Haber process. Remember, that's our process for the creation of ammonia from hydrogen gas and nitrogen gas. So imagine that this reaction is at equilibrium. So if the reaction's at equilibrium, but then we disturb the equilibrium by increasing the pressure in the reaction container. So in a practical sense, that could be that we, for example, smash the existing gases into a smaller volume. All right, that would be an equivalent thing to increasing the pressure in the container. Pressure, where does pressure of gases come from? So maybe it'll help us a little bit if we can at least in a roundabout way define what pressure of a gas actually is. So pressure has something to do with push, right? What's pushing on what to create pressure?
Everything in that container.
Yeah, everything in that container. So all of these gases are creating a push on the walls of the container. The higher the pressure, the more push there is. Does that make sense? All right. So what I want you to think about is where that push is actually coming from. Something is happening with those individual molecules as they're in that container to create the push on the walls. What are those individual molecules doing to create a push on the walls of the container to create the pressure? Sure, I guess in a roundabout way. So those molecules are flying around inside that container, right? And eventually they get stopped by colliding with the wall of the container. Those collisions are actually what's responsible for creating that push. So the more collisions with the wall of the container, the higher the pressure inside that container. All right. So let's analyze this disturbance the same way we've analyzed all of our other disturbances related to Le Chatelier's principle. All right. Le Chatelier's principle, in the most roundabout sense, tells us whenever a reaction at equilibrium is disturbed, the reaction acts to counteract the disturbance. All right. So I can't remember the exact terminology that was used in your lab, but it's like stress, response to stress, or stress offset, right? So the stress here is the reaction we've increased the pressure in the container. What would the offset to increasing the pressure be then? Decreasing the pressure, right? So the reaction is going to want to respond to an increase in pressure by decreasing the pressure in the container. Whenever we do the reaction to throw it out of balance, the reaction tries to make the opposite thing happen. So we know the response to this stress is going to be that the reaction is going to act to decrease the pressure in the container. All right, we increase the pressure to mess it up. The reaction is going to try and do the opposite, to decrease the pressure. Is there a direction that this reaction can shift that would cause a decrease in pressure? Now think about where pressure comes from. All right, it comes from collisions of the gas molecules with the walls of the container. Well, it's the same number of atoms because that's an atom balance chemical equation. But there is a difference on the two sides of the equation here, how many gas molecules there are around. On the left-hand side of this equation, I see 4 moles worth of gas. On the right-hand side of this equation, I only see 2 moles of gas. There are less moles of gas molecules in the products than there are in the reactants. So if we shifted our equilibrium to the right, if we made more products, that would decrease the total number of moles of gas in the container, which would mean that our pressure would decrease. So stress, response, shift. This is kind of the same way that we've written about all of those in the lab for this week. All right. Our stress is we increase the pressure. We know the response to that is going to be the opposite. The reaction is going to act to decrease the pressure. And then which direction is this reaction going to shift to accomplish that response? Now, because pressure comes from moles of gas, more moles of gas means more pressure. Shifting to the side with less moles of gas means that the reaction is going to be decreasing its pressure when it shifts to the right. That's actually also a super useful thing to do to understand how the Haber process works the way it does. All right. So if we wanted to make as much ammonia as possible, the product of the Haber process, would we rather run that reaction at a lower pressure or a higher pressure? Higher. The higher we can make our pressure, the more we push the reaction toward making more ammonia, more products. We want it to be as cold as we possibly can run it at while it still runs efficiently. If we run the reaction cold enough, then the conversion of N2 and H2 to NH3, the rate of that conversion slows down too much. It becomes too slow. All right. That is not an equilibrium problem. That's a kinetics problem. Okay. We always have to think about both things when we're doing any reaction on an industrial scale. We have to think about the final position of the equilibrium when it settles out. And that's what we're talking about with Le Chatelier's principle. We also have to think about how fast are we going to actually get to equilibrium. So temperature definitely plays a role in how we design the Haber process. And if we could run it at any temperature and it would still run efficiently, we would run it at as low a temperature as possible. And the reason why is because this is an exothermic reaction. In other words, heat is a product of this reaction. Whenever we turn these two things into NH3, heat is a byproduct of that reaction. So since heat is a product of the reaction, the lower we run our temperature at, the more we are pushing the reaction to make more heat to replace the heat that we're taking away. Does that make sense?
Yeah.
Yeah. So that's why we want to run the Haber process at as low a temperature as we possibly can.
Okay.
And then pressurize it as much as we possibly can. And the other thing we also do is, as ammonia is made, we take it out. So removing some of the products of the reaction is also a stress. If the reaction's at equilibrium and it's made as much NH3 as we can use, as we can make, we take some ammonia out, and what does the reaction do? It shifts to the right to make more ammonia to replace the stuff we took out.
Because when we take it out, we reduce the pressure, right?
Well, yes, it also reduces the pressure, but the bigger issue is it changes the concentration of product, right? By removing some product, the reaction is now not in balance anymore, so we make more product to replace the product we took out. So all three of those disturbances to equilibrium are hacks that we use to run the Haber process in as efficient a way as possible. Make as much ammonia as we possibly can as quick as we can. Because the world needs lots of ammonia to fertilize all of its world fields. Any more questions about Le Chatelier's principle? So up to this point, we've learned about like the mathematical way that equilibrium is modeled with the equilibrium constant K, right? We learned that the equilibrium constant always represents concentrations of products over concentrations of reactants. And we learned in a more specific way that whenever we look at a balanced chemical equation, when we're talking about products over reactants, the coefficients in the balanced equation become exponents in the equilibrium expression. All right? Just reminding you guys of all that because we haven't seen it in like a week at this point. So what I want to get back to is this idea of using math to model the position of equilibrium in a chemical reaction. So actually using the equilibrium constant to solve problems to do with equilibrium. All right? It's not hard because we already know how to write an equilibrium expression. It's just like using it and doing some algebra with it from there on out. Believe it or not, that kind of math is going to take us through like most of the rest of this class, using K to solve problems. Yeah, it may sound bad at first, but it's really good because once you get the hang of it, it gets easy because we do the same things over and over again. All we're doing is applying them to different chemical systems. All right. I don't know how chemistry teachers teach this and then teach like each one of the equilibrium chapters like it's like a brand new thing. There are some extra things that we think about in each of those chapters, but we're using K to solve those problems every time. And using K in very similar ways. So it's going to get easy on us. At least that's my fervent hope for all of us. So what I want to do is I want to look at this assignment. Oh, those are good ones too. I'm going to publish those. These are just practice problems to do with equilibrium. I had us look at some equilibrium introduction problems last time that we were actually thinking about equilibrium together. So it looks like we didn't get to all of those, but that's totally okay. All right. We'll do a couple of them as review problems. And if you guys want to get to the same problem that we're in right now, we're in the 1018 intro to equilibrium assignment. All right, number 6 from that assignment, right here. Number 6 from the 1018 equilibrium practice assignment. Regardless, even if you don't want to follow along, we can at least propose an answer for us to try on the board up here. So what are we thinking? Which one of those matches up with the correct value for K here? Remember, K is always products over reactants, and the coefficients in the balance equation become exponents in the equilibrium expression. Intriguing. So you have magnesium chloride in the denominator here because it's a reactant, but you may have forgotten something pretty important. Look at what magnesium chloride is in terms of its state of matter. It's a solid. Solids and liquids do not show up in equilibrium expressions because we're always talking about concentrations of things when we're talking about equilibrium. And if we were to evaluate the concentration of solid magnesium chloride, it would be a constant anyway. All right, so we don't worry about that as part of the balance between reactants and products. So it looks like out of the ones that have just a 1 for the denominator, this is the one where the exponents match up with what we see from the coefficients in the balance equation. All right, magnesium 2+, there's only one of those, and magnesium 2+ is to the first power. There are 2 Cl minuses, and Cl minus is squared in the equilibrium expression. So it turns out that even in this like super introductory question to do with evaluating the proper K for a reaction, what we've done in looking at this particular expression is looked at a specialty version of an equilibrium constant. That K is not generally referred to as KEQ or K sub C, which are the most general equilibrium constant things that we use, the most general kinds of K. This is actually a very special K, all right? So you'll hear me talk about special Ks all the time, all right? So depending on how old you are, that might mean something to do with drug culture or something to do with like cereal, right? Special K is also like a formulation of ketamine, which is a party drug. Yeah. Also very useful for rewiring people who have like serious medication resistant depression cases sometimes. Yeah. Or massive doses of magic mushrooms, which is actually a lot safer than ketamine. They're honestly, they're very similar chemically for what they do to your brain. Yeah. When he had to have magic mushrooms for breaking his wrist. Oh, okay. It could. They could, if you could extract the active compounds from the mushrooms and put them into a shot to shoot a horse up with them, then it would work just as well as ketamine. Most animals don't like to eat magic mushrooms because they taste pretty bitter. Yeah. Taste doesn't equate to edibility for mushrooms at all. There are plenty of like deadly toxic mushrooms that are really flavorful, delicious tasting mushrooms. Yeah. Lots of dogs die because they eat mushrooms that are deadly toxic, but it's because they're tasty. Yeah. And dogs are just vacuum cleaners, they eat everything. You won't hear me say bad things about magic mushrooms because honestly, the most dangerous part about magic mushrooms is the possibility of misidentifying mushrooms when you're trying to get magic mushrooms. But that's an education issue, not a problem with the mushrooms themselves. And we will, every once in a while, instead of using regular Ks where molar concentrations represent our products over reactants, we will use K sub P instead. The only difference is, instead of talking about molarities of products over reactants, K sub P uses pressures, partial pressures of products and reactants. So in a case like this, I think we did this one together already. NO2 and H2O are our products. So you can see that in the correct answer, which is 1 here, our partial pressure of NO2 is raised to the 4th power because there are 4 NO2s in the products. Our partial pressure of H2O is raised to the 6th power because there are 6 H2Os in the products. H2O is weird because like very often we ignore it in equilibrium expressions because H2O is often a liquid, but at the right temperature it can also be a gas and show up in equilibrium expressions. All right, so you have to watch what the state of matter is for those things that you're trying to write an equilibrium expression. So anyway, 1 is the best one of those. I don't know, 7? Which one? So we have a partial pressure of V to the 1st power. So we should only see 1 V in the products. Right, we do. We have a partial pressure of A to the 2nd power, which means we should see 2 A's in the reactants. We do. But there's other stuff. Oh, it looks like B and C are both solids. So we would expect neither one of those to show up in the equilibrium expression. Yeah, that looks good to me. One more quick one. This should only take a minute or two. We're looking for something that has 3 C's in the products and 1 A in the reactants. All right. So B is out immediately. If we look closer at the C's here, these 3 C's are liquid, so that couldn't be right because then those C's wouldn't show up as part of the equilibrium expression. So we're down to A and C as answers here. let's look over at the A part of the reactants. And it looks like only in letter C is our reactant A aqueous, something that should show up in the equilibrium expression. So C, answer C is the only one that ends up with this equilibrium expression. The others are all something else. If this one's confusing, and it probably will be, what I want you to do is actually write out the K sub P for the first reaction. All right, you know how to write out a K for a reaction. And if you don't want to do it in partial pressures, just do it with molarities. That's fine. All right, write out the K for that first reaction. And then after that, write the K for the second reaction. So we'll call the K for the first reaction K1. And we'll call the K for the second reaction K2. All right, write me a molar equilibrium constant K for this reaction, and then another one for this reaction. What would K1 look like? The K for the first reaction. And it could be molarities, it's fine. C to the third over. What? B having B to the first power? Okay. For the second one, that is a perfectly acceptable response. For the second, we have C, and there are 9 of those, so we'd have C to the 9th power, right? And we'd have A to the 6th power, and we'd have B cubed. This is kind of one of those like, hey, got ya, jokey kinds of questions. It's a neat relationship, but one that might be a little hard to see the first time you look at it. If I rearrange this mathematically, all of these exponents are divisible by 3, which means that I could factor out C to the third times A, or divided by A to the second, and B to the first. And that entire thing would have to be raised to the 3rd power to get K2. Does that make sense? So if that's the case, then we can define the K for the second reaction as the K for the first reaction to the 3rd power. Does that make sense? It's just taking advantage of the relationships that you see when you write out the Ks for those two, all right? They're related to one another because this right here on the inside of the parentheses, that is the K for the first reaction, and we'd have to cube that to get the K for the second reaction. Just taking advantage of the relationships that we see. So They defined their K for the first reaction as K sub P. So we know that the K for the second reaction is the K sub P for the third product. Let's look at one more of those, paying careful attention to the relationships. All right. Now, it's kind of hard because I don't even give you any reaction. So if I don't give you a reaction, I suppose you can make one up. What if we were talking about this reaction right here? You can't get much simpler than A reversibly turning into B. If you were writing the K for that reaction and both of those things were gases, we would have K is equal to the molarity of B divided by the molarity of A, right? And we know the value of K for this reaction under these conditions is 2.54. The reverse of this reaction would be B turning into A. And the K for that reaction would be the molarity of A divided by the molarity of B. So, is there a way we can relate the K of the second reaction to the information we know about the K of the first reaction? It absolutely is. All right. So we know that the K for the second reaction is 1 over the K for the first reaction. We take the first reaction's ratio of B over A, and we get the reciprocal of that to get the ratio of A over B. So 1 divided by 2.54, I have no idea what that is, but whatever that answer is going to be the K of the reverse reaction. Give me 3 sig figs. There we go. Now, we're going to start thinking about actual chemical reactions and using the value of K to solve problems. And this will be a good first experiment with that. It's going to teach us some principles that'll come in really handy for lots of problems. I'm going to make this slightly smaller so that I have a little bit more. Not that. This slightly smaller. Have a little more space. So this reaction tells us that the K for when we dissolve CuCl into water to make Cu plus and Cl minus. And note that anytime we're talking about a solid dissolving in water, that is one of our special kinds of K. We normally call it a KSP because we're talking about the solubility of a salt. We're given a value of K for this reaction of 1.00 times 10 to the minus 6. And we're asked, what is the molarity of copper plus going to be at equilibrium? First of all, I want you to think about the size of K here. What does the size of K tell us about the balance between products and reactants for this reaction? Is K a big number? Is a small number? Very small. What that tells us is that this reaction is very reactant heavy at equilibrium. We're going to have a lot more reactants than products anytime there's a K that's a really small number. If we had a K that was a huge number, we would have a lot more products and a lot less reactants. So we know right away that because this K is really small, the amount of copper 1 chloride that actually dissolves to make ions is going to be tiny, right? There's not going to be very much copper plus or Cl minus at equilibrium because K is small. But how do we know exactly how much Cu plus we're going to have when we get to equilibrium? It's a really hard question, but I want to address it in a theoretical way, all right? And this is a sort of global standard way that we have of teaching equilibrium. It seems to make sense to tons of students. So what I want to do is I want to track what this reaction looks like right at the beginning, all right? So what we're going to do is we're going to figure out what the molarity of all the important things in this reaction are initially before we get to equilibrium. And then we're going to think about how this reaction is going to have to change to get to equilibrium. In other words, which direction we got to go. And then finally, we will define what the molarities look like at equilibrium. Now, if we were writing the expression for KSP for this reaction, what would it look like? How would we calculate the KSP for this reaction? Cu plus, the molarity of Cu plus, times the molarity of Cl minus. And the reason why that is because CuCl, the reactant, is a solid. It doesn't show up in the equilibrium expression. So when we are defining our initial concentration of CuCl solid, we're not giving a crap about that because CuCl is a solid. Its concentration is irrelevant to the equilibrium. But when we very, very first put that copper 1 chloride into solution, before the reaction has had a chance to get to equilibrium, we can assume that at the very instant that that copper 1 chloride touches the water, none of that copper 1 chloride has dissolved to make copper plus or Cl minus yet. So we're going to say that initially we don't have any Cu plus or Cl minus in this reaction. The molarity of both of them is 0 at the beginning. Now we're going to identify a change to get to equilibrium. This is an easy change to predict because what has to happen in order for us to get to equilibrium if currently we have none of the copper plus or the Cl minus in solution? Yeah, we have to create some products to get to equilibrium, right? We can't go any lower than 0. We've got to have some concentration of Cu plus and Cl minus at equilibrium. Do we know the exact molarity of either one of them that we need to get to equilibrium? No. So here is where we have to use our mathematical brains a little bit to define the change to get to equilibrium in a way that makes sense. If we don't know how much Cu plus and Cl minus we need to get to equilibrium, let's use a variable to talk about how much Cu plus or Cl minus we need to get to equilibrium. And let's say that we have to create X molarity of Cu plus to get to equilibrium. Now, the cool thing is that if we have to make X molarity of Cu plus to get to equilibrium, Because of the formula of CuCl, we know that every time we create 1 molarity of Cu plus, for every 1 mole of Cu plus we create in solution, we also create 1 mole of Cl minus, right? So if our molarity of Cu plus to get to equilibrium is X molar, and we'll call this plus X because that's how much we're creating, we're going to end up creating the exact same molarity of Cl minus. We don't know what X is yet, but we're defining that as how much Cu plus and Cl minus we need to make to get to equilibrium. And because when we split apart CuCl, we get 1 of each of those things, that's how we know that at equilibrium, those concentrations have to be the same as one another. Whenever we create of one, we create the exact same molarity of the other. So at equilibrium, our molarity of Cu plus is going to be X moles per liter, and our equilibrium of Cl minus is also going to be X moles per liter. Now, all we have to do to solve this problem, to solve for our final concentration of Cu plus, is substitute what we have defined as our equilibrium conditions into our equilibrium expression. So the KSP for this reaction is 1.00 times 10 to the minus 6. And we know that that equilibrium constant is equal to our concentration of Cu plus times our concentration of Cl minus at equilibrium. Well, let's substitute in how we've defined those concentrations in our problem here. 1.00 times 10 to the minus 6 is equal to X times X, or X squared. So solving that expression for X, we find that X equals 1.00 times 10 to the minus 3. And that means that the molarity of Cu plus at equilibrium has to be 1.00 times 10 to the minus 3 mole. We've defined X as our final concentration of Cu plus at equilibrium. We will see this language used like 100 times now, defining where the reaction is at the beginning, identifying the change that we need to make to get to equilibrium, and by doing those things, we can define, using a variable normally, what the equilibrium concentration of a reactant or product is going to look like. That is how we can use our equilibrium constants to solve problems. So, I'm going to ask you a quick question. Does this answer make any sense? Is that a large concentration of copper plus? No. No. All right. 1 millimolar, 1/1000th of a molar. That's a very low concentration. We anticipated that that would be a really low concentration because the K for the reaction is a small number. In other words, we don't expect a lot of products once we get to equilibrium. You guys want to try another one like this?
Yeah, I'm confused on the, X over X.
X over X? There is no X over X. Yeah. Initially, we have none, and then we add X more to get to equilibrium. You do. I square rooted both sides. I think I can do that using my exponent math in my head. Well, let's do it this way. So one easy way to do this is do 1 times 10 to the minus 6. And then I'm going to raise that quantity to the 0.5 power. That's the same thing as square rooting it. That's 1 times 10 to the minus 3. You can look at how your calculator or how you're putting in your digits to your calculator. Hey, another ad pop up for this stupid calculator app. If it wasn't so darn useful, I would have deinstalled it already. So maybe I'll look and see if I can find a paid version so those go away. But I did take the square root of both sides. Yeah, I just did it in my head. Let's try another one of these. So I think the homework should let you put it in either way. It should let you put it in as 0.00100. And the reason why it did that is because our K value has 3 significant figures in it. So I'm reporting 3 significant figures for my concentration. In scientific notation? Yeah. So in scientific notation, we would type it in as 1.00 times 10 to the minus 3. It should work either way. Yeah, and look, I'm putting it in the non-scientific notation way now. Good. Yeah. So let's do a problem of my creation that is very, very similar here. Oh boy, what just happened? Hey, Google, what's the KSP of barium sulfate? Oh, no, that's not a good one. I don't like that. Hey, Google, what is the KSP of calcium hydroxide? Perfect. So the KSP for this chemical equation is 5.02 times 10 to the minus 6. All right, that's the K for dissolving calcium hydroxide in water. Yep, 5.02 times 10 to the minus 6. And we've been at it for an hour, so let's take a break for a few minutes. Daniel had the right idea. He was just a little bit ahead. And he left. Yeah. I need a greater thing to put this to that in front of it. I've been there one since like before. And then when I got over here, I didn't even have a break. I had a meeting with the chemistry department. I said I was 5 minutes late for them. They hate whoever they assign this class to. Not because you guys are bad, but just because it absolutely destroys whatever chemistry professor's schedule ends up getting this class. Because it has Monday afternoon classes and that conflicts with our normal institutional meeting times and stuff like that.
That's not really like normal. It's really every other day,
No.
5 days a week.
Ooh, there's that little tea station in the middle of this room. I wonder if they have any people up there. I might know that's not the case.
Like when I'm doing having the future, like the other way. So I was like nervous and shaky, and I'm like, are you doing this right? Like, it's like, no, I'm actually not nervous, but I'm using this without you. It's a weird feeling. I noticed that when I was doing like several copies and then doing like 2014, I was just kind of doing it. I was felt nervous. Only when I felt maybe not, I was like, I was like, it's so weird. I'm not really
I would love to take it still, because but my family has my brother, my mom, and I do not have a diagnosis.
You don't want to either.
I don't want to, but it's more than we not doing a good job. And I don't. I tried a non-chemo medication, and it's been sick. Do you feel fine without medication for that? I haven't either. It's been about a month, but it's taken I was there. And then yeah, I started taking on. I was doing some really like living now. That was what it is. Who's heard of it? It's stories out there. Like when I got off of it, I didn't.
You
No, exactly.
one of my boys actually, haven't, we never considered meditating them, we try like diet and other stuff. But the movie part, I think we don't do it too. Because it's like coffee and then fire. It's really nice, like, that is relatively good.
And I agree that it's really common for people to like different vaccines.
Yeah, it's like, no big difference in coffee, but. And then.
I do it for you. Yeah, sometimes it's caffeine, I feel like that, but then I think it's better to like that and that. So I don't even know.
Some people get wired by Benadryl.
Yeah. On your time long, I should have given it to them at home to try it out first. That was fun.
So if we were establishing initial concentrations at the very beginning, when we first throw some solid calcium hydroxide into water to get it to try and dissolve, what would our initial concentrations of calcium 2 plus and OH minus be? 0. We haven't dissolved any of either one of them yet. Which means that to get to equilibrium, since our K is not 0, we're going to have to dissolve some of our calcium hydroxide. We're going to have to make some calcium 2 plus ions and some hydroxide ions to get to equilibrium. So let's think about the change that we need to get to an equilibrium state here. If we define our change in concentration of calcium 2 plus ions, all right, the increase in concentration of calcium 2 plus that we need to get to equilibrium, if we define that as X molarity, how would we have to define our change in hydroxide to get to molarity? Yeah, or colloquially, we call it 2X. Because whatever molarity every time we dissolve a calcium hydroxide in solution, we get 1 calcium 2 plus ion and we get 2 hydroxides. So whatever increase in molarity of calcium 2 plus we get, automatically the increase in molarity of hydroxide will be twice that big. That's why we define this change as 2X, because we know whatever molarity increase in calcium 2 plus we have, the increase in OH minus molarity is going to be twice as big. So at equilibrium, our molarity of calcium 2 plus can be defined as X, and our molarity of hydroxide should be able to be defined as 2X. Does that make sense to everybody? Now, all we have to do to solve this problem of what the final molarity of hydroxide is in this solution of calcium hydroxide is substitute these concentrations into the equilibrium expression. All right, so if we were to write the KSP expression for this reaction, our calcium 2 plus, the first product, is to the first power because there's only one of them. Our hydroxide concentration is squared because there are 2 of them. Now let's substitute what we know are our equilibrium concentrations of each of those things from our table. All right. We often refer to these kinds of initial change equilibrium tables. We call them ICE tables. I guess you probably can get why we call them ICE tables. So our value of KSP is 5.02 times 10 to the minus 6. We've defined our equilibrium concentration of calcium 2 plus as X. We've defined our equilibrium concentration of hydroxide as 2X. So this is the expression that we need to solve for the final molarity of hydroxide, which is defined as not X, but 2X, right? 2X is our final molar concentration of hydroxide in the solution. When I simplify the right-hand side of this equation, what do I get? Be careful. Algebra can bite you in the tush here. Is what? What is 2x times 2x? 4x squared, right? 2x times 2x is 4x squared. And then we multiply that by another x. So the right-hand side of that equation simplifies to 4x to the third. And that is what's equal to 5.02 times 10 to the minus 6. Remember to distribute when you multiply. The distributive property has consequences. Yeah. I love our Wednesdays in class. Having a couple of hours is like enough time to actually delve into a topic deeply and learn things. Not like Mondays where we've got 40 minutes left after lab. So to solve, we would divide both sides of the equation by 4 and then take the cube root of both sides, right? Well, I'll show you a way to do it. And this calculator looks very, very much like the TI calculators. So that's 5.02 times 10 to the minus 6. I'm going to divide that by 4. All right. So I get 1.255 times 10 to the minus 6 is equal to x cubed. And we have to watch a video in order to continue using our calculator app. Oh my God. So I have to take this number and take the cube root of it to get my answer. All right. That is the same as raising that number to the 1/3 power. That's the way that I do it. So I'm going to take that number and raise it to the, and then in parentheses, 1/3 power. Raising something to the 1/3 power is the same thing as taking the cube root of it. All right. Taking the square root is the same as raising something to the 1/2 power. We can even like support that with a mathematical expression here. If I were to do something to isolate x on the right-hand side of this equation, the way that I would do that is take x cubed and raise it to the 1/3 power. So because we essentially multiply exponents when we have a like base, x to the third to the 1/3 is just x. So whatever we do to one side, we have to do to the other side, which means that this to the 1/3 ends up being x. So I'm calculating x as 0.0108 molar, or at least that's my value of x to three significant figures. If I've defined my concentration of hydroxide at equilibrium as 2x, then 2x is equal to 0.0216. So that should be the molarity of hydroxide that I would expect in the solution once it reaches equilibrium. So now that you've seen this method of initial and change in equilibrium, let's try and solve some more problems using equilibrium expressions. Okay. I unlocked a couple of very small problem sets to look at for us. All right. 1018 intra equilibrium. There are a couple of other ones that so the 1017 one was also one that I just published today, I think. These are all old problem sets. They're essentially just like practice problems that I used at some time or another last time I got to class. So I'm going to rename this 1025 practice B. I'm not going through these in any particular order. I'm just looking for ones that look like they might be fun to tackle for us right now. It looks like practice B is kind of where we need to be right now. All right. So think about this one carefully. Both these reactions are happening in the same vessel. In other words, A can turn into B, or A can turn into C. And those are the values of K for the reactions. Which of those three things will there be the most of in the solution? And if you guess, you got a 33% chance of getting it right. But I want a clear rationale for why you picked the one that you picked, because there is a clear rationale here, right? What does the size of that first K tell you? Is it a big number or a small number? Okay. Nope. Remember, K is the ratio of products over reactants. So if K is a small number, it favors reactants, right? What about the second K? Big number or small number? Still small. So does that reaction favor reactants or products? All right. So both of those reactions favor reactants. What's the reactant in both reactions? So what are we going to have the most of in that container? Yeah, we're going to have the most A in that container because both those reactions favor reactants over products. Yeah, we're not trying to solve anything here. We're just evaluating based on the values of equilibrium constant. All right. So I'm going to ask this question, and you're probably not going to know exactly how to answer it. All right. And that's okay. The reason I'm asking this question is because it's going to allow us to develop a way to answer questions like this that's really useful. So in the couple of problems that we've looked at already today, it was really easy to tell which direction the reaction had to go to get to equilibrium. Because with those couple of KSP problems, what we started with was none of the solid dissolved. Right? We knew we had to make products to get to equilibrium. What if we're in a situation where we start off with some reactants and some products? In that kind of situation, it can be really hard to tell which direction we have to go to get to equilibrium. All right? So let's analyze this reaction and see if we can come up with a way of telling which direction the reaction has to go to get to equilibrium. The reaction we're looking at is two NO2s in equilibrium with N2O4. And the K, the P for the reaction is 0.25. All right. So in the reaction, it tells us that right now, our pressure of NO2 is 0.50 atm. And right now, our pressure of N2O4 is 0.25 atm. So this number tells us what equilibrium looks like for this reaction. So we know that based on how we've defined our equilibrium constant, our partial pressure of N2O4 divided by our partial pressure of NO2 squared, that ratio should equal 0.25 at equilibrium. Right? Isn't that what the equilibrium constant tells us? That at equilibrium, the ratio of products over reactants should be 0.25. So it might be interesting for us to look at where we're at right now instead of at equilibrium. We define our ratio of products over reactants, where we're at right now, a lot of chemists will use Q to describe that. And I'm using Q sub P because we're talking about a K with pressures. So Q is just a term that we use that we solve the same way that we solve for equilibrium, except we're using it with the concentrations that we have right now instead of at an equilibrium state. So let's see where we are at in terms of a balance between products and reactants right now in the reaction. So right now, our partial pressure of N2O4 is 0.25 atmospheres. Right now, our partial pressure of NO2 is 0.50 atmospheres. But because of how we calculate the denominator there, because there are two of those NO2s in the denominator, our 0.50 gets squared when we're talking about calculating it as an equilibrium quantity. So we're calculating the balance of products over reactants right now in the reaction, not at equilibrium. All right, we're calculating and know that that ratio should be 0.25 at equilibrium. We're seeing where it is right now. So what do we get when we divide 0.25 by 0.50 squared? So 0.5 times 0.5 is 0.25, right? Yeah. So right now, our Q value, our where we're at compared to equilibrium is 1. In other words, our Q, the position of our equilibrium right now, is greater than the value of K for the reaction. That tells us something. If we calculate where we're at right now, that tells us that our ratio of products over reactants right now has more products in it than we will have at equilibrium, right? If Q is bigger than K, then what we've identified is that in our current state, our reaction is not at equilibrium because there are too many products present, or not enough reactants, or both. So which direction is this reaction going to have to go to get from a Q of 1 to a Q of 0.25? In other words, to be at equilibrium. If we make more products, our Q is going to get even bigger. Okay, yeah, there's only two possibilities. All right, right now, our ratio of products over reactants has too many products in it. So we need to shift to the left. We need to make more reactants to get to equilibrium. This way of assessing the balance of products over reactants in a reaction right now, instead of at equilibrium, that's when we use that variable Q, all right? It's just an abstract concept and it's often referred to as the reaction quotient, because chemists have to make a name for everything. So calculating Q allows us to compare our ratio of products over reactants at any point in the reaction and compare that to the value of K, which represents that ratio at an equilibrium state. So we discovered here that since Q, the current ratio of products over reactants, was higher than K, we know we've got too many products right now. We need to shift to the left and make more reactants to get to equilibrium. Calculating Q is the easiest way to know which direction you have to go to get to equilibrium. Why didn't we have to calculate Q for the first couple of reactions that we did? Because we know that our K was not 0, which meant that we had to make some products to get to the equilibrium state, right? We immediately knew that our Q was smaller than K, because there were no products at all, right? If there are no products, you got to make some products to get to equilibrium. So let's see if we have assessed correctly here, all right? We said that the reaction needs to shift in the reverse direction to get to equilibrium. Awesome. Which one of these encapsulates what Q means the best? So if we calculated Q and it was equal to K for the reaction. Okay. Well, there are two answers there that say the reaction's at equilibrium. All right. Either the reaction's at equilibrium and it stops, or the reaction's at equilibrium, which means that it proceeds in equal rates in forward and reverse. That is the correct definition. All right. Remember that equilibrium doesn't mean reaction stops. It just means that we're creating products at the same rate as products are being turned back into reactants. We call that dynamic equilibrium. Good job. All right, so we didn't forget about that. So I've thrown a few questions to help us assess our retention of Le Chatelier's principle into the mix here. Those are gases. So another way of saying the same thing that we're saying in this problem, if we increased our container's volume by a factor of 2, what does that do to the pressure in the container at the same time? Yeah. All right, the more we squeeze the gases into a smaller space, the more we increase their pressure. So if we increase the volume, that would be the same as decreasing the pressure here. All right, so the reaction is disturbed by decreasing its pressure. What will that do to the direction the reaction is going to want to shift? Try and write out a 3-step approach here, right? What's the disturbance, or what's the stress? What's the response to the stress? Which direction would the reaction go to respond? So stress is we've decreased the pressure. What's the response that the reaction is going to go for? What's the reaction going to try and do in response to that? Has to try and increase its pressure. How do reactions increase the pressure in their container? More pressure would come from more moles of gas. There are more moles of gas in the reactants than in the products. So that's why we're pushing for making more reactants here. Because more moles of gas, which is on the reactant side, would increase the pressure, which would offset the disturbance. For delta H of the reaction, is less than 0. In other words, delta H is negative. This is an exothermic reaction. That's what that delta H being a negative sign tells us. It's nice delta. In reality, they should have made that a subscript. That's normal, is to have a delta H and then in subscripts reaction. But I think that they might have problems putting subscripts in some places here because their states of matter are most often given as subscripts, and they don't do that either. Active in them, right? So for an exothermic reaction, is heat a reactant or a product for an exothermic reaction? It's a product. So if we just write heat in as an unofficial product of this reaction, if the reaction's at equilibrium, but then we increase the temperature, all right, increased temperature is the stress. What would the response that the reaction would try and do then? If the stress is an increase in temperature, the reaction is going to try and lower its temperature. So how would this reaction lower its temperature? Yeah. All right. Or you could say by using up heat, consuming heat. We certainly wouldn't want to produce more heat, which is what we would get by making more products, right? Instead, we would do the opposite. We would consume that extra heat by turning the heat back into reactants. Because if the forward reaction is an exothermic reaction, in other words, it produces heat, the reverse reaction is an endothermic reaction. It sucks heat in. So we could lower the temperature by creating more reactants here. Oh, somebody already answered. Good. I like that you're following along and running ahead. Stress. We are removing H2 gas from the reaction. Response. Whatever we do to the reaction to screw up the equilibrium, the reaction is going to try and do the opposite thing. If we remove some H2, the reaction is going to try to make more H2 to replace the stuff that was lost. Which direction would this reaction shift to make more H2? Yeah, it would make more products. Don't know why they put the hydroxide ion over there on the right as HO minus, but that's OH minus, the hydroxide ion. Bro. if we added 1 drop of aqueous sodium hydroxide, which direction is that going to shift our equilibrium here? Yeah, stress is adding NaOH would increase our concentration of hydroxide. Does that make sense? All right, so by adding NaOH, we've increased our concentration of hydroxide. The response to that is the reaction is going to try to get rid of hydroxide, to decrease the hydroxide concentration. So how can we decrease our hydroxide concentration? We shift to the left. We turn some of that hydroxide back into water and NH3. I might have an answer. I don't remember what the reaction was anymore. So there are no precipitates here. So all that means is that some of that hydroxide gets used to make H2O and ammonia instead. Believe it or not, this represents another kind of buffer solution right here. So buffer solutions generally are formed anytime we have both a base and a conjugate acid in solution together at the same time. All right, so the reason why the pH would read a certain pH in the solution has to do with how much H3O plus there is in the solution. All right, and it also has to do with OH minus concentration in the solution, because if you know one in an aqueous solution, you automatically know the other. So the cool thing is that if we add some more OH minus, which would normally make the pH of a solution go up quite a bit. So you saw that when you added NaOH to water in the lab, the pH skyrocketed, right? Went way, way up. So if we added OH minus to water, the pH changes a lot. It goes way up. If we add OH minus to this buffer solution, the pH doesn't change that much. And the reason why is because most of the OH minus that we add to this solution doesn't stay in the water as OH minus. It gets turned back into water and NH3 instead. Yep. That's how buffers work. They take any extra OH minus and turn them back into water, or they take any extra H plus and turn that back into water instead. There isn't anything to turn the OH minus into in water. Yeah, there's no reaction that we can use to get rid of excess OH minus if we just put OH minus into water. It just stays there, and the pH spikes. Yep. So buffer solutions are capable of neutralizing, of getting rid of excess OH minus in the solution or excess H plus. So HCl, when we dissolve that into pure water, the pH went from like whatever it was, 6 down to 1 or something like that, right? HCl made our pH of the regular water plummet downward. But when we put a little bit of HCl into the buffer solution, the pH didn't change very much at all. That's because all of the excess H plus that we were adding by adding HCl to the solution got turned into other stuff because of the buffer. You would certainly make it less inclusion. Yeah, you can overwhelm a buffer eventually. Because eventually, in this case, what would happen is if we added enough OH minus, we would run out of NH4 to use to react with it, right? Eventually, we wouldn't have any more NH4 plus, and the buffer would run out of capacity at that point. Yep. That's what happens when you get acidified blood and you die. When your blood's buffering capacity runs out. And it doesn't take, I mean, a pH change of just a couple tenths of a unit in your blood is enough to keep data. Blood's really good at buffering pH. From really high concentrations of carbon dioxide in your blood, for one. So, yeah. What do you mean? In your blood? How does that happen? It may be urea, not ammonia. So urea is sort of like one of the ways that your body tends to try and eliminate excess nitrogen from the things that you eat. All right. And if your kidneys are working properly, they can excrete lots of urea in your urine. So here's the chemical structure of urea. And you'll see why it's a really efficient way to get rid of excess nitrogen.
But even if it's not filtered correctly, then it goes up.
Yep. And urea, it definitely does increase the pH of things that it's in. It's a pretty basic molecule. The same way that hydroxide is a base, urea is also a base. Not nearly as strong a base as hydroxide is, but strong enough to increase the pH of blood by quite a bit. So I think I'll let you guys ruminate on the Le Chatelier's questions from the lab. What I want to spend our last few minutes on today is actually the lab before that, because now you have enough information to actually be able to do a good job at solving for the final concentration of ions in that weak acid solution. All right. So remember, you did dilution math to figure out the lowest concentration of those two different solvent or solutes that would make the bell ring, essentially. Remember that? Okay. So does anybody want to volunteer their answers for those two measurements? And your answers are all going to be different because you were using different devices. Detection limit. The instrument detection limit. I haven't graded it yet because I didn't want you to turn it in yet.
Yeah.
I want your concentrations that you calculated for each of those two things. For the NaCl, so you started at what, 0.1 molar, and then you diluted to some final concentration. And you started at 0.1 molar acetic acid, and you diluted to a final molarity of acetic acid. So I want the final molarities of each of those, the lowest concentrations of each of those that still produced a detection, still produced a sound like you were seeing ions in the solution. I don't need all of your lab notes for how you did the dilutions. Just hopefully you trust those dilution calculations well enough now.
That's my calculation. I don't have my computer and fairly good my molarity to see what kind of flip around with acetic acid being smaller molarity, and then NaOH being a molarity.
You mean NaCl?
NaCl.
Yeah, that's weird. You should definitely be able to detect a much lower concentration of sodium chloride. Did Daniel, was your data like that? Did you detect a smaller concentration of NaCl?
No, I wouldn't think so. I think it was
I have a smaller concentration of CHEM.
Okay. What was your concentration of NaCl that you ended up with?
Like 0.0061.
And what was your final concentration of acetic acid that produced that detection?
0.0065.
All right.
That's where it stopped. That's where the
That's close enough. Because at some point between before and after that dilution was where it cut out. So that's close enough. If it was me, I would have probably reported the data point before that, like the last one where you actually heard it. What were those? For the NaCl. Wow, that's a huge jump downward.
Yeah,
Okay.
I did it different on the second one, so that's so big, so I was working with it still.
Okay. Yeah, I would hope that we'd be able to get a little bit closer to a threshold than like a factor of 100 or something like that.
Yeah.
All right. So what was your last one that registered for the acetic acid?
0.00237.
Wow, that's hardly a difference at all. So you were really making small changes there.
I was trying to do
That's good. All right, that's what we want. So that is a really dialed in. If you knew that that produced a sound and that didn't, that's really good.
Okay.
All right, that's like all-star caliber. We have honed in on the exact place where our detection limit is now. All right, that's a very small change to go from here to here and to go from I can sense the ions here, I can't sense them here.
Okay.
Perfect. All right. Hopefully, if you were to do the lab over, you would get to a place where you would have that level of surety about this data point too. All right. That's what I was hoping you guys would get from your procedure. But we'll just use these two data points for right now. We'll use this one as close as you've got. All right. And we'll use this one as close as you've got. So if I was calculating the total concentration of ions that got detected for this one, it's really easy because we know that sodium chloride is soluble in water. In other words, at least until we can actually see sodium chloride, salt, coming out of the water as a precipitate, we know that every bit of NaCl that we put into water splits apart into Na pluses and Cl minuses, right? So if our concentration, and we're going to say that this is all aqueous at this point, if our concentration of NaCl is 0.000625 molar, for every one NaCl that we put into the solution, we get 2 ions, right? Whatever our molarity of NaCl is, our molarity of ions has to be twice that big because we get 2 ions out for every one NaCl that's dissolved. So I would multiply this by 2 to get my total molarity of ions in the solution. That's easy. It's easy because sodium chloride completely splits apart in water. The next calculation is a lot harder because acetic acid is not a strong acid. It's a weak acid. In other words, it does not completely split apart in water. So we have to figure out what the final concentration of the ions is in this solution of acetic acid And here is how acetic acid reacts when we put it into water. Acetic acid reacts with water to make H3O plus ions and acetate ions. We call that liquid water. And that acetic acid is aqueous. So this is the reaction that shows how our acetic acid turns into ions in solution. That's why we detect ions in a solution of acetic acid, because some of it turns into H3O plus and acetate. I have no idea why the negative sign didn't show up there. And this reaction is an equilibrium. The Ka value for that reaction is 1.8 times 10 to the minus 5. In other words, this reaction is very reactant heavy. Not many products get made. So what I want to do is use what we've learned about equilibrium math today and try and solve for the equilibrium concentration of ions in this solution. You know what the final concentration of acetic acid was. We're going to put that in, all right, as our initial concentration of acetic acid in the solution, 0.00237 molar. And we're putting that in as an initial concentration because we know some of that is going to react with water to make ions, but we don't know how much yet. So since right now, at the very beginning of our reaction, we haven't made any H3O plus, and we haven't made any acetate, what would our change look like to get to equilibrium here? Yeah, we're going to create some molarity of H3O plus and some molarity of acetate. We don't know what that molarity is yet, so we'll define it with a variable, all right? Whatever molarity of H3O plus we end up with, because there's a 1-to-1 mole ratio in our reaction, we know that we're going to end up with the exact same molarity of acetate. The other thing that we have to worry about right now, though, is that there is a molarity of acetic acid that we have to worry about. Whatever the molarity that we add of H3O plus and acetate, we also are taking away that much molarity of acetic acid because it's a 1-to-1-to-1 mole ratio, right? For every mole of this we create, we have to get rid of 1 mole of this. So at equilibrium, my molarity of acetic acid is going to be 0.00237 minus X. And my molarity of H3O plus will be X. And my molarity of acetate will be X. To solve for our final molarities of those two ions in solution, to solve for X, we just have to substitute into the equilibrium expression. So we know that the Ka for this reaction is our molarity of H3O plus times our molarity of acetate divided by our molarity of acetic acid. Water doesn't show up because it's a liquid, not part of the equilibrium. So let's substitute everything that we know from our ice table into the equilibrium expression. Ka is 1.8 times 10 to the minus 5 for this reaction. It's a number you can look up in a book. Our equilibrium concentration of H3O plus is X. Our equilibrium concentration of acetate is X. And our equilibrium concentration of acetic acid is 0.00237 minus. So we probably won't have time to actually get to the solution for x today unless you guys want to stay over. But this is an algebraic expression that we can solve for x. It turns out that it's not like the easiest expression to solve for x ever. We got to use a little bit of like quadratic math. All right, this is polynomials math. But it's not impossible. It's just algebra. It is also possible for us to use our calculators to solve problems like this pretty efficiently. So I'll give you some tricks for that as well. All right. But once we know what x is, x plus x would be the total concentration of ions in that solution. And if I am right, and if we did a really careful job at getting to the closest that we could to the breaking point, the detection limit, I think that the total concentration of ions from those two different solutions should end up being really similar numbers if you did a good job with finding the breaking point. All right, we're starting to use equilibrium expressions to solve problems now, like what concentration of ions is left over in the solution because it's a weak acid. We'll do a lot more equilibrium kinds of problems the next time that we're together. We do not have lab scheduled for next week because next week is a non-instructional day for both campuses. So it's they call it an institutional day, which is like catch-ups for meetings and stuff. Do you guys have classes scheduled right now for next week, Monday? Yeah. So the real crapper of it all is if you are, I'm gonna show you something. Also, I'm gonna complain a little bit about administrators, and hopefully you won't pass those complaints on. So when I go to schedule my classes at the beginning of the quarter and like figure out what my course schedule is going to look like week to week, here's the first place I go: academics, and then academic calendar. So listed here should be every university holiday or every college holiday for the quarter, right? It is, because there aren't that many this quarter. So fall 2023. This was not on the calendar at the beginning of the quarter. So when all of us made our schedules, we assumed that October 30th would be a regular instructional day. And then the administrators were like, wait, we needed that institutional day for a lot of meetings. So they put it in after the quarter started. I am thinking about trying to do something where I create not a 2-hour lecture video because I think I'm going to stay on the history of the world, but maybe a couple of topical videos that I'll have you guys watch instead of coming to a class that day, where we just look at some more examples of using K to solve problems. So I'll work some problems using K and then talk through the thought process for that. All right. That way we don't completely lose that time that I was counting on for us, because we already need all the time we forget. But they already have a schedule for all kinds of incredibly exciting, wonderful, useful meetings for that day. So we're not allowed to have class that day.
So, oh, and then it was around. Okay.
In an hour.
Right. He's in Denmark. Unfortunately, he's having to take care of his mother. So, and there's a giant storm that took out like a bunch of the islands he's on. That's all. So he probably
Such an interesting food.
yeah. He doesn't even each other think about it.
He might have been, so this retcon of, oh yeah, we actually do have an institutional day on October 30th. There was an email sent out about that for us like a week ago. Yeah, so he probably doesn't even know that there's an institutional day scheduled for that day. The email said something like, they were pretty insistent about it, so they said, if you've scheduled class, and if missing that class time would be a large hindrance to your students, like, have a discussion with your dean about it. When it's have a discussion with your dean about it, it normally means they're gonna tell you you're skipping class that day. I think that's right, yeah. No. I think it's actually like a Friday or something. We'll look at that right now. Yeah, it's a Friday. But it does affect my CHEM301 who has their labs on Friday. But it's all right. We'll get enough labs in by then.
I redid the test questions. And then at the end of your video, you said only do the ones you missed. It's just practice, but you don't need to go back and rewrite them all and do them again.
Yeah, you don't need to correct one. No,
I rewrote them though. It's like one I.
Oh, you're talking about on the correction.
Yeah.
You just redid them anyway. I'll find the ones.
Well, I wrote next to it, like,
Okay.
Correction.
Okay, yeah, I'll figure it out.
I can rewrite it and just put those.
Totally.
Like one of them I got like a -7, so I was like,
Okay.
Yeah.
Still correct it.
yeah, so I was like, well, this is one.
Yeah, you can still correct it.
I just didn't want it to be like a test, if we didn't follow that completely.
Yeah, there'll be a box for it. I haven't opened the box yet.
Take pictures the same way.
Yes, absolutely. And Daniel, I was reminded of something. I was actually super bummed that I had to take off points because you did all of the questions. So I actually gave you a 2-point break somewhere else in the exam. Like I was, one might say more than lenient in interpreting one of your answers. So for you're welcome. So I'm just telling you, like, I was sensitive to that ahead of time. I just have been so sick that I didn't remember being sensitive when I actually talked to you about it later. So I already made a sort of unofficial like offset for that penalty because it ended up biting you so hard. If you look at the question that was your limiting reactant stoichiometry question, I think I gave you all 10 points for that. And the work was all really good, but in the first part of it, it asked how many grams of product would be the theoretical yield, and you gave the amount of product in moles instead. So you missed one conversion factor. I know you knew how to do it because you converted grams and moles bunches of times correctly other places, but I should have only given you like 8 out of 10 for that question. I gave you all.
Okay, so now it's different than the original one you gave me that now, or?
No, it's just that you got more credit for that question than you would have originally. So it ended up because you got 10 points on more than one question, then you got 2 more points on your exam than you would have if I had graded partially for all of the questions. So there was essentially what I'm saying is there was already a 2-point offset to your score that offsets some of the difference in score that you would have gotten based on having skipped one question. So assuming you skipped your 4-point question, then that would have meant that your total score on the exam would be 6 points higher. I gave you 2 points back through an unofficial channel already. And you'll get more of the points back when you do the correction. So it's not going to be that.
Yeah. So you get half a point for every sorry, half of the points.
Maybe.
Back.
So I actually haven't said that officially yet, but most of the time that's what I do for the first exam. Is if you do the correction very well and give me like the correct work and the principles that lead to the right answers, I normally give up to half the credit. All right. And you didn't lose all of that credit because I sort of like unofficially kicked a couple of points your way somewhere else because I felt bad about it. Yeah. And I did it for that purpose, but I was just so sick like I've been so out of it because of taking cold medicine constantly. Like I literally forgot that I made an allowance already sort of unofficially correct for the fact that that was a pretty harsh penalty. I just wanted to let you know that I did that for you. And you're welcome.
So, yeah, that part, I mean, I